Now we are going to talk about reaction heat dynamics. So the first thing we have to look for is the total change in enthalpy. And that's basically delta H, that's enthalpy change, and that's total energy change in reactions. It's referred to as heat of reaction, and sign of delta H for a reaction, whether it's positive or negative, it indicates the direction in which energy is exchanged and is determined from the perspective of system. When we talk about whether delta H is positive or negative, we are talking from the perspective of system. So it could be endothermic process where you have energy input, you are giving energy to the system, and delta H is going to be positive in this case. It receives energy from the surrounding, while a negative delta H indicates that the system decreased in energy. It gave its energy to the surrounding, okay? So there's some energy release occurs. So both of these cases, when I say energy input and energy release, we are talking about from the system perspective. So this direction of energy exchange is described by the terms endothermic and exothermic. So when I'm saying exchange, because all of this is about system interacting with surroundings. So for example, when I say energy release, obviously from system perspective, so the energy is released from the system and absorbed by the surrounding. So if we have delta H for surroundings, they are going to be with opposite signs. All of this can be best described by thermodynamic energy profile of the reaction. It's basically 2D graph of reaction progress versus potential energy. And this is just one example. So as you can see on y-axis, we have enthalpy. In some other thermodynamic energy profile, you can see potential energy. So for this specific purpose of chemical systems, the reaction thermodynamic, thermochemistry, it's not very important to distinguish potential energy and enthalpy. And here on x-axis, we have reaction coordinate. You can think of it as time. So it's basically progress of reaction. We are starting from starting materials and going to products through transition state. So this highest point, which corresponds to transition state, is energy maxima. This is local maxima here. And we need some kind of activation energy in order to reach transition state. And then we are going to products. And in this specific graph, the energy of products are lower than the energy of starting materials. So net result here is that we are giving energy to the surrounding. So this reaction is, let's say, labeled as exothermic reaction. On the other hand, we could have endothermic reaction where the energy of the products are higher than the energy of starting materials. So this reaction is endothermic. So that means that they have received some kind of energy from the surroundings, and it looks like this. Here you can see that energy goes down, so that means some of the energy is released to the surrounding as Q. So you can represent it as Q, and starting materials are lower in energy in compared to the energy of products, so you need to supply some amount of energy. So you can write it like this. So in order to compensate that gap. All right, and now we continue, and students are often confused by the sign of delta H because there is like physics perspective and the chemist perspective. In physics, the signs are reverse of those shown in the previous slide because physicists think of delta H in terms of surroundings rather than the system. They care about how devices, how the systems have an impact on the environment, on the surrounding, how much work the device can perform. Chemists, on the other hand, they are interested in the reaction, chemical system. When chemists run the reaction, they care about the reactants and the products. They do not care about how reaction ever so slightly change the temperature in the laboratory. For example, you conduct a reaction, energy is released. So we assume that this flask is the system, right? So if this reaction that's happening in the flask is exothermic reaction, it's going to release energy to the surrounding. But then that surrounding we define as anything outside the reaction, right? So it's basically the whole laboratory, whole universe outside that reaction flask. But then that energy release is gonna slightly affect the energy of the surrounding. Maybe 0.0001 degrees Celsius increase in temperature of the laboratory would be observed, which is extremely negligible. So reason why we have different sign when we talk in physics and in chemistry is because different perspective. In physics, it's surrounding perspective. In chemistry, it is system perspective. Now we are continuing with an example. So you have some reaction. This is, by the way, substitution reaction. We have alkane and the chlorine. You need some kind of HV, which means light energy, in order to make this reaction happen. This is free radical chlorination. And now we have to identify whether this reaction is endothermic or exothermic. So the first thing we have to do is, because up until now we only know what happens when we break the bond and form the bond, right? Whenever we break the bond, so you have to remember this graph. This graph should always guide you distance here, and you have energy, and you can use simple H2 molecule. So you can start reading graph from the right hand side, and this is like two hydrogen molecules are separated on a distance and then they come together. So this is like two hydrogen with their one electron separated by large distance. So no interaction at all. We accept this interaction as zero energy, and then they come, and then here they make a bond. So basically hydrogen molecule H2. And as you can see, the energy of hydrogen bond is some negative value. As far as I remember, it was 435 kilojoule per mole of hydrogen molecule that's being formed. And now here it's zero, right? So you are basically decreasing energy when you go from atoms to molecules. So this two hydrogen going to H2, you basically go from here to here. You are going lower in energy. So that means you are releasing some energy, right? So plus Q. So delta H is going to be less than 0. This is going to be negative. This is exothermic reaction. So when you form a bond, you release energy. Now let's think about the opposite case here. Opposite case would be dissociation reaction, where you have a hydrogen molecule, and now you have to go from this point back to the atoms. So the reaction would be H2 is going to 2H, right? And now you have to supply some amount of energy, because now you are in minus 435. You need to supply the same amount in order to go to 0, basically. And by the way, this 0 and minus 435, it's relative. So just for convenience, we just accept that the two hydrogen with no interaction with each other, separated by large infinite distance, have 0 energy. And for this reaction, H2 going to 2H, you need to supply some amount of energy. So delta H is going to be higher than 0. It's going to be endothermic reaction. So you always have to remember this graph. You have to keep this in mind in order to immediately answer whenever someone asks you, is bond breaking endothermic or exothermic? And now you are finding out which bonds are broken and which bonds are formed. Basically, you can go through all bonds, but we have to be efficient here. You see that this CH3, 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 they are kept intact. So nothing happens. So you don't have to include them in your calculations. There is no need for them to be included. So you only care about the differences. So what I see here is that CH bond is being broken. I don't have any CH bond here, and chlorine-chlorine is broken because I don't have any chlorine-chlorine bond in my product. And this C-chlorine bond, we didn't have any in the reactant, so it's formed, and HCl is formed. So you always have broken bonds in your reactants, obviously, and formed bonds in your products. And then you look up the table of bond dissociation energies. How much energy is required in order to break a bond? So that's the basically definition of bond dissociation energy, because we supply energy in order to break a bond. So bond dissociation energy, which is defined as the energy required in order to break a bond, is a positive value. So you can find this in appendix or some kind of table, and you look up them and you just find that, okay, in order to break this bond, I need to supply this amount of energy, so on. And in case of forming a bond, you are changing the sign of this. You are going to put a negative if we are talking about bond forming. Now we have identified which bonds are broken, which bonds are formed, and we have the associated values with them. Now we can continue. So we are taking those values and we are having this kind of procedure. So is a bond broken? So yes. If that's the case, delta H is positive. So we just basically copy paste the values here from BDE values. And if the bond is formed, then the delta H is negative. We are gonna take the negative of the value we are seeing here and we sum them up. That's it. And what we get here is basically this. We convert this table into more comprehensive one with positive and negative values. Negative for the formed bonds and positive for the broken bonds. And we sum them up, and that's gonna be delta H of the reaction. If you want to put them into formula, you can write delta H reaction is equal to sum of the bond dissociation energy in the reactants minus sum of the bond dissociation energies in the products.